The final set of circuits that we look at for balancing are active balancing circuits that use inductors at their core for how they work. The first one that we see is a switch transformer design, and this one here can move a lot of charge at once. Uh, the transformer down there is the active component, and I'm sure you know that a transformer has, at least an ideal transformer, has power in equals power out, and power in is voltage times current, and a transformer can have windings such that I can increase or decrease voltage while at the same time decreasing or increasing current. We have this transformer primary windings connected to the entire battery pack or module of a battery pack. So this here is high voltage or higher voltage, and then we have an n-to-1 winding ratio, so I have lower voltage here on the secondary, so I have low current, but I have high current here. So unlike the capacitor designs where the amount of balancing current was severely limited by a voltage difference, here we can actually amplify current taken out of the entire stack and put that current back into a single cell. So I'm pulling current out of all of the cells and I'm putting current back into one cell only. So I'm bringing all of them down a little bit, but one of them up quite a lot in terms of state of charge. That's the basic idea, and we can do it quite quickly because of that. Now, transformers don't work with DC. They work only with AC, and ideally they work with a pure sinusoid. But they also do work with a chopped sinusoid. So what this circuit is doing with this switch here is, maybe I'll draw it this way, is it's turning voltage on and off the primary of the transformer, and the DC level of that voltage is rejected, but the AC amount, if you think about this as a Fourier series, there's a strong AC fundamental frequency and then a few secondary frequencies also that go through this, and it makes up on the other side something that's probably not quite a square wave, but it's maybe a rounded square wave on the other side. On the other side, it would not have a DC offset because the DC is rejected by the transformer. That's why we have a diode here. The diode makes sure that I am only putting charge into a cell. I am not removing charge from a cell by reverse biasing the cell. That would be bad. So as long as the transformer output voltage is bigger than the voltage of a cell, there's going to be current that goes into it. Otherwise, there isn't. So we still get a lot of current when the peaks of these voltages from the transformer are above the cell voltage. There's some intelligence in this because I have to decide which cells to select. So I have to say, what does this switching network here do? But besides that, this other control is very simple. It's just always on, off, on, off, on, off to chop the DC to turn it into AC. So I think we said this. The primary is connected across N cells in a module or battery pack. The transformer is wound with an n-to-1 ratio, and the output of the transformer is decreased in voltage by a factor of n. So from n cells down to a one cell comfortable voltage, that's good. But the current is increased by a factor of n, which is also good for us. And the diode plus switches select the cell into which the charge is dumped. This is much more efficient than passive balancing. It's much faster than capacitive methods, but sadly it's also expensive because the transformer is a relatively expensive part. We can make capacitors on chip. We can make inductors on chip, but only small ones, and transformers on chip, again, only really small ones. So to make a transformer that can handle a lot of current, you'd really need to have a discrete device. It's heavy, it has a lot of iron in it usually for the core and so forth. So active balancers, while they have some great advantages, also have significant cost. And the control of the switching and so forth is also fairly expensive. But there are some silicon vendors that I've talked with, and they're all out there. They're all working on automated controls for active balancing designs. I think the market will eventually move that way with larger and larger battery packs, because for a very large battery pack for a very large electric vehicle, the passive balancing isn't going to work. The heat rating, the power rating on the resistors would be too high. It would not be feasible. So there's a trade-off at some point between cost of a passive balancing resistor, believe it or not, and this active balancing circuitry. And so silicon vendors are preparing themselves in order to make the chipsets that are required for this. Another possibility for active balancing that is much simpler in terms of the controls is the one that's shown here. And again, the primary of a transformer is connected to a module or the entire battery pack. But in this case, there are multiple secondaries. So we have a custom wound transformer, and all of these are N to 1. So I have a multi-tap transformer, if you want to think of it that way. And I'm just always turning it on and off, on and off. So the control is dead simple. And basically, this is going to be a voltage-based method, but it's pumping current, so that whenever the voltage on the secondary through the diode is greater than a cell voltage, it's going to charge that cell. But because it's more voltage-based than the other one, it is also going to be somewhat limited in how fast it works. A quite recent design in active balancing is this last one, and I'm one of a project team working on this design right now, but the leads are at Utah State University and University of Colorado Boulder for the electronics design and modeling and so forth. And I tried to show this picture here that's cut out of one of the papers that we've written on this subject. Might be better to go look at the paper because the picture isn't very good. Maybe I'll zoom in a little bit here and see if that helps at all. A little bit. This here is showing, with the red boxes, a bunch of battery cells. And on the right there's this green thing, which is a low voltage bus. And we have the high voltage bus, which is connected to the load. That's over here. So the plus and minus, that's your normal voltage, high voltage of your battery pack. And you've got all the cells connected in series. This low voltage bus is something that's a little bit different. And you could think of it, at least for now, as just two wires that have some kind of energy storage, like a capacitor, between them. If one cell has a higher state of charge than the other cells, what it will do is it will move charge from that cell into the low voltage bus using a DC-DC converter. So on the right here we have a zoom. So there we see I've got one cell, I've got an isolated DC-DC converter between that cell and this low voltage bus. Sounds complicated. It actually is complicated. But there are some advantages to this design that make it actually pretty cool. This low voltage bus is not a constant voltage. Especially if you think about it as a capacitor, if I put charge onto this bus, I'm raising the voltage, and if I remove charge from the bus, I'm lowering the voltage. So I can move charge both ways, at least in principle, through this DC-DC converter. And we can make this work without communication from cell to cell, from DC-DC converter to another one. And that saves a lot of cost. If I can remove the communication interface, there's a lot of components and isolation and complexity associated with that. And the way this works, at least in principle, is suppose I've got a DC-DC, this low voltage bus that can range between 9 to 14 volts, roughly speaking. And I make a mapping between the bus voltage and my cell voltage, or my cell SOC. So if I compute my cell SOC, and based on this mapping, that's a 10 between 9 and 14. I compare that 10 to the voltage on the DC-DC bus. If I'm above the DC bus voltage, I pump charge into the bus. If I'm below the voltage, I pump charge out of the bus. So this capacitor here, or this bus voltage, is a single analog communication channel that is kind of the average of all the states of charge, or all the voltages, or whatever metric you want to use, of all of the cells in the battery pack. And if this cell is higher than the average, I'm going to pump charge into the bus, and if it's lower than the average, I'm going to pump charge out of the bus. That's the general idea. So is that what I said here? Primary problem with active balancing is its costs. I'm proposing to you a solution here which seems like it's going to cost more, but hang on. Suspend disbelief for a few more minutes and we'll get to why this can actually be low cost. We're going to put one small DC-DC converter parallel to each cell, and a capacitive shared low voltage bus is used to share information and to perform the balancing. And so a balancing metric, whether it's state of charge or if it's cell voltage or whatever that metric happens to be, is mapped to a DC level between 9 volts and 14 volts. And this metric might be designed to promote differential power processing so that I would increase stress on strong cells versus weak cells. So we could come up with a clever metric based on this present state of charge of the cell and the present resistance of this cell and the present capacity of the cell. We come up with some mapping between 9 and 14 volts that will basically say if this is a healthy cell or a weak cell, and it will take charge out of a healthy cell and put charge into a weak cell, essentially, in order to put less stress on the weak cell. So we enhance life, and ultimately we bring the entire pack to a homogeneous end of life by doing this. So the principle of operation, as I've said, is we transfer charge from a low voltage shared bus to the cell. If the cell's metric is below the shared bus voltage, we transfer charge from the cell to the low voltage shared bus if this cell's metric is above the shared bus voltage. The general design of the DC-DC converter is shown here. This is a fairly generic DC-DC circuit where the isolated converter uses a transformer design, so it kind of fits in with this inductive methodology that we've looked at. But on the primary side, we have an H-bridge controller, which you turn on these two transistors at the same time to make charge go one way through the transformer, or these two at the same time to make charge go the other way through the transformer. And on the other side, you do the same kind of thing with these pairs of transistors. And then we have the shared bus voltage and capacitance there, and then here we have some controls that are placed on both sides of the bus to make all of this magic happen. So I've got a V cell, I've got a V bus over here, and I've got that DC-DC converter in between. Now, this sounds really expensive. There are some design simplifications. One of them is the 9 volts to 14 volts of this secondary bus here was not chosen arbitrarily. This 9 to 14 volts is roughly the voltage range of a standard lead-acid battery. And in electric vehicles nowadays, we have the high voltage battery pack, but we still keep the nominally 12 volt lead-acid battery. in the system because it runs all of the electronics in the car. We haven't done away with that. So maybe we can replace some aspects of that lead acid battery if we produce 9 to 14 volts ourselves. Maybe we can power auxiliary loads from the low voltage bus. We can power the heaters in your nice leather seats. We can power the windshield wipers, the headlights. We can power the entertainment system. We can power your anti-lock brakes. We can power all of these things from this low voltage bus. And if the load power is large enough and consistent enough, I don't need a bidirectional DC-DC converter here. I simply need a unidirectional DC-DC converter, which always goes from the high voltage cells to the auxiliary bus, and that saves some design effort and makes the design more efficient as well. So that cuts some costs. And notice that we're not processing the total power of a cell when I say we direct more power to a strong cell versus a weak cell. We're only processing the mismatch power through this system. We're taking a little bit extra load off of a strong cell versus a weak cell, and that makes the electronics a lot less expensive also. So it turns out that the overall solution can be better than cost neutral compared to passive balancing. So this can actually be less expensive than passive balancing because, one, it balances, which we need to do, but two, we replace a very costly component that's already in the vehicle system. So right now we have the high voltage battery pack and we have the low voltage lead acid battery. And in between, in present cars, we have a DC to a DC converter which connects these two. With this present design here, this goes away. That very high cost component goes away. This is basically the alternator in an existing PHEV type of car. They don't have an alternator. They power the high voltage pack, and then from the high voltage pack they power the low voltage pack. So it's kind of like an alternator that you're doing away with by using this interesting balancing topology. So anyway, this has been demonstrated at this point in history, and we are undergoing some extensive life testing at National Renewable Energy Labs to see if this is a really practical, viable, long-term thing like we hope it is, and maybe someday this will be in your car.